Hello everyone, welcome to the Tomilo live stream. I'm the host Yu Nguyen. Today, we have the honor of inviting an expert in the battery field, Senior Product Manager Wang, to provide in-depth answers to many questions our customers are very concerned about regarding battery safety. Hello, Wang.
Hello.
First of all, thank you very much, Wang, for taking the time to participate in our technical interview today. So, for this interview, I've also done some preparation and learned some questions that our customers are very concerned about from the sales team. Let's start with the most basic question. What are the standards for safe batteries?
When it comes to these standards, we first need to pay attention to the core national standard for batteries, GB 38031, 2025. In this national standard, the updated requirement for batteries is that, after thermal runaway, they must not catch fire or explode, and an alarm must be triggered within 5 minutes in advance. This standard is very strict regarding battery safety requirements.
Okay, the high safety requirements of our new national standards are indeed impressive. So, from a technical perspective, what are the main causes of battery thermal runaway?
Battery thermal runaway is mainly caused by 3 major factors. Firstly, mechanical abuse, such as battery deformation caused by collisions. Secondly, electrical abuse. For example, internal short circuits caused by overcharging. Thirdly, thermal abuse, such as battery material decomposition caused by sustained high temperatures, leading to thermal runaway.
Okay, so thermal runaway is caused by these 3 factors. How terrifying is the process of thermal runaway?
The main triggering factors for thermal runaway include mechanical damage, overcharging, internal short circuits, etc. Under the influence of these factors, the active materials within lithium-ion batteries undergo intense exothermic reactions. When the internal temperature exceeds controllable limits, thermal runaway ultimately occurs. The exothermic chemical reactions inside lithium-ion batteries include the decomposition of the solid electrolyte interface, say film, reactions between the anode active material and the electrolyte, and the oxidative decomposition of the electrolyte. During the charging and discharging processes, ethylene carbonate reacts with the anode at the phase interface of the electrode active materials, forming an say film on the graphite surface. This film can directly slow down or even prevent reactions between the electrolyte and the active materials on both electrodes, significantly reducing the exothermic reaction rate and enhancing the stability of the cathode and anode materials.
When the temperature rises to 90 to 120 degrees Celsius, the say film begins to decompose,
followed by exothermic reactions between the electrolyte and the anode active material. As the exothermic reactions proceed, the internal temperature of the battery gradually increases. Depending on the separator material used, the melting point varies. For example, polypropylene separators have a melting point of 165 degrees Celsius, while polyethylene separators melt at 135 degrees Celsius. When the melting point of the separator material is reached, localized shrinkage occurs, causing direct contact between the cathode and anode materials and resulting in a short circuit, which generates substantial heat. The heat generated by the short circuit further accelerates separator shrinkage, intensifying the exothermic reactions. Simultaneously, within the temperature range where the say film decomposes and exothermic reactions occur, lithium salts also undergo vigorous exothermic reactions with the electrolyte. Common active materials in lithium-ion batteries include lithium hexafluorophosphate, LiPF6, and lithium tetrafluoroborate, LiBF4. At high temperatures, LiPF6 decomposes into phosphorus fluoride, which further reacts with the solvent, extracting oxygen atoms from carbon-oxygen bonds, and triggering intense exothermic reactions that accelerate electrolyte decomposition. Additionally, the redox reaction between LiPF6 and the solvent releases highly toxic hydrogen fluoride gas. Within the same temperature range, the electrolyte itself decomposes, releasing small amounts of flammable gases. Studies show that the gases produced by electrolyte decomposition primarily consist of ethylene, carbon dioxide, and hydrogen. The rapid vaporization of the electrolyte increases internal pressure. When the internal pressure reaches the limit of the pressure relief valve, large quantities of flammable gases are released, further exacerbating the spread of thermal runaway.
The entire process of thermal runaway is divided into 5 stages. Firstly, at 60 degrees Celsius, the electrolyte decomposes. Then, at 80 degrees Celsius, the safe film ruptures. At 170 degrees Celsius, the positive electrode begins to decompose, producing oxygen. Subsequently, at 230 degrees Celsius, the electrolyte catches fire. Finally, the binder decomposes. At each stage, a large amount of flammable gas is produced.
Okay, 1. Our users are very concerned about the specific development process of thermal runaway. Do we need to take different protective measures at different stages?
We have formulated corresponding preventive measures based on different levels of thermal runaway.
So, how are these safety levels classified? And who classifies them?
The safety levels are mainly classified by the European Automobile Committee, with a total of 8 levels, ranging from 0 to 7. Level 0 means the battery has no functional loss, belonging to level 0. Level 1 means the battery has some reversible loss, meaning it has not undergone thermal runaway, nor does it have any defects or faults. It just temporarily loses its original function and can be reused by simply resetting the battery's protective device. This belongs to level 1. Level 2 indicates irreversible damage, requiring repair of the battery to restore it to a usable state. Level 3 means there may be some leakage, and we have also set a requirement for the leakage amount. That is, when the electrolyte leakage is less than 50%, it belongs to level 3 thermal runaway. When the electrolyte leakage exceeds 50%, it belongs to level 4, a dangerous level. When the battery undergoes thermal runaway and catches fire, it corresponds to level 5. When the battery ruptures and its casing breaks, it belongs to level 6. What is level 7? Level 7 means the battery directly explodes. The requirement in the national standard that it must not catch fire or explode corresponds to the minimum requirement in our safety levels, which is up to level 4, corresponding to the safety protection for levels 0 to 7. We also have some safety measures during testing for levels 0 to 4. We only take protective measures because thermal runaway has not occurred, just some leakage has occurred. At this time, we will equip the device with acoustic optical alarms, like door hinges and pressure relief devices. For levels 5 and above, we will equip gas detection sensors, smoke detection sensors, and even fire extinguishing devices to prevent the spread of thermal runaway.
I see. So, I've heard that there are many types of fires. What type of fire does battery combustion belong to?
Battery combustion is relatively complex. The battery contains electrolyte, which is a liquid, so it belongs to a liquid fire. Its casing and materials are solid, so it also belongs to a solid fire. The battery itself is also an electrified object, so its combustion also belongs to an electrical fire. When it burns, it produces a large amount of gas, which is mainly a gas fire. It is mainly composed of these four major fire types.
Okay, so there are these types. So, which fire extinguishing method is the most effective?
For this comprehensive fire, there are mainly two relatively effective fire extinguishing methods. The first one is heptafluoroprone fire extinguishing. However, this fire extinguishing agent is slightly toxic, and when sprayed, it is in a firm state, which is difficult to clean up. The second method is perfluorohexane, which is an environmentally friendly agent. It is sprayed in a water mist state, which is relatively easy to clean up. This is also the most commonly used fire extinguishing method currently.
Okay, got it. Thank you, Wang, for your patient explanations. Now let's move on to another topic. What new tests have been added to the national standard to ensure battery safety?
The national standard has mainly modified the content of environmental testing with 3 key points. The first point is the overcharging test in the cell test, which must be charged at 1.5 times the rated voltage for 30 minutes to ensure the battery does not catch fire. The second point is the thermal diffusion test at the battery pack level. For thermal runaway at the battery pack level, it must trigger thermal runaway in a single cell, trigger an alarm within 5 minutes, and keep the temperature of adjacent cells below 200 degrees Celsius. The third point is our top priority, which is the safety test. It includes 7 cell tests and 17 overall pack tests. The third point is the environmental test, which involves freezing at minus 30 degrees Celsius for 12 hours, followed by immediate 3C fast charging testing. A high-quality battery pack can still maintain a charging efficiency of over 85% at low temperatures.
Okay, so for such strict safety requirements, what tests do we need to perform on the battery to ensure its safety? Please provide a systematic explanation.
according to the requirements of GB 3803120-5. The entire testing system is divided into 3 major categories. The first one is the aging life test, which simulates a 3-year usage cycle and conducts 300 fast charging cycles. After cycling, the battery must still pass the external short circuit test without catching fire. The second one is the short-term electrical performance test, which includes overcharging, over-discharging tests, and external short circuit tests. The third point is the core of our discussion today, the safety and reliability test. This is also a top priority test, which includes 7 cell tests and 17 battery pack tests.
So, what tests do customers typically perform using our environmental chambers?
Generally, when customers choose our environmental chambers, they opt for chambers ranging from -40 degrees Celsius to 100 degrees Celsius. The battery needs to undergo the following 3 major categories of tests. The first one is the low-temperature cold start test, where the battery is placed in a -30 degrees Celsius environment for 12 hours, and then immediately subjected to fast charging testing. The second one is the high-temperature storage test, where the battery is continuously placed in an 85 degrees Celsius environment for 72 hours. The third one is the temperature cycling test, where the temperature changes once every hour in an environment ranging from -40 degrees Celsius to 85 degrees Celsius for a total of 10 cycles.
These 3 testing dimensions, aging life, short-term electrical performance, and safety reliability, together constitute our comprehensive evaluation of battery safety performance. Through these rigorous tests, we can ensure the safety and reliability of batteries under various extreme conditions. Thank you, Wang, for your detailed explanations today. I hope today's explanations have given everyone a deeper understanding of battery safety. See you in our next interview.